It's a pleasure to introduce our speaker for today, Eric Rosenthal. Eric is a PhD student at the University of Colorado in Boulder, working with Professor Conrad Leonard at JILA. Eric got his bachelor's and master's in physics from the University of Pennsylvania in 2015. And he's been, since then, doing a lot of really cool work in superconducting systems, in particular looking at measurement noise and backaction. So he's going to talk today about his PhD work. So Eric, great to have you. Looking forward to your talk.
Derek, thank you for the kind introduction. So hi everyone. It's a pleasure to be here today virtually. And as Derek said, I'm Eric Rosenthal from JILA and the University of Colorado Boulder. Today, I'll be speaking about our work on improving the measurement of superconducting qubits. And this is motivated by a desire to improve and scale up quantum computers using this technology. Before we begin, I'd like to thank the many other people involved in this work, both at JILA and our collaborators elsewhere. And in particular, I'd like to thank my advisor, Conrad Leonard. For those of you who may not be familiar, Conrad's group has many different projects spanning from optomechanics to microwave to optics conversion to searching for axion dark matter. But what maybe ties these all together is if you go to the lab website, the header says, the Leonard Laboratory, researching the ultimate limits of measurement. You might ask yourself, what does improving quantum computers have to do with some sort of ultimate limit on measurement? By the end of the talk, I hope to answer this question and show you how we can engineer systems to approach such limits. To yourselves, qubit measurement needs no introduction, but allow me to give a brief definition, which we'll return to later with more nuance. So pictured here is the block sphere. Every point on the surface of the sphere represents a qubit in a pure state. For example, the superposition state shown by this blue arrow. When we projectively measure the qubit, its state is collapsed onto either the 0 or the 1 eigenstate. Simple enough. Of course, we, as experimenters, also have to control some physical process which maps this collapsed eigenstate onto one classical bit of information on our lab computer. And it's entirely possible that this mapping doesn't work as intended. Perhaps the bits highlighted in red here are actually chosen randomly, not correlated with the qubit state. And in any quantum algorithm, we of course want to eliminate these errors. To make progress on doing so, let's first take a moment to remind ourselves how conventional superconducting qubit measurement works. And this begins with the qubits themselves. So these qubits are anharmonic inductor capacitor resonators with a microwave resonance frequency. Anharmonic meaning that some nonlinearity has been added from a Josephson junction so that the energy levels of the oscillator are no longer evenly spaced. And we take the lowest two and address them as a qubit. How exactly this works is a beautiful story developed over a decade ago now. But for this talk, it's really sufficient to think of the qubit as simply a two-level system described by the first term in the Hamiltonian here. This qubit is almost always dispersively coupled to a second linear resonator. And so the red box here represents this qubit resonator system in the dispersive limit. Dispersive meaning that the coupling between the qubit and resonator G is much smaller than their detuning. In this limit, and the Hamiltonian for this combined system has a term for the qubit, the resonator, and then their interaction, which is parametrized by this frequency chi. We can think of this interaction term as meaning that the resonator frequency is shifted by plus or minus chi depending on the state of the qubit. And so assuming chi is not too small compared to the resonator line width, then for example, if say this resonator has two ports and we measure in transmission near its frequency, we expect to see a different response depending on if the qubit has been prepared in the ground or the excited state, like shown here. And so to measure the superconducting qubit, we will scatter a pulse off of the readout resonator and measure the phase or the amplitude of that scattered pulse, which will encode information about the qubit state. But the catch is that this pulse typically contains only a few microwave photons. Too many photons in our model breaks down. And this is extremely weak by the standard of any conventional electronics. We have to have about 100 dB of amplification between this qubit cavity system and our digitizer at room temperature. And so our problem of qubit measurement has really been mapped onto how well we can measure this weak pulse. And so to place our work in context today, we are going to use a standard superconducting qubit, a transmon qubit, as you call it, in this standard dispersive architecture. The unconventional part of our experiment is how we go about measuring this weak readout signal. And to appreciate that further, let's take another minute to review how conventional superconducting qubit measurement works. So in all of these experiments, including our own, the readout pulse is measured using a quantum limited parametric amplifier. Quantum limited in practice meaning that the added noise of the amplifier is still small compared to our few photon readout signal. Now, in typical experiments, the qubit is protected from the destructive effects of amplifier backaction by use of ferrite circulators or isolators. These are magnetic devices which enforce the unidirectional flow of information in a network. Now, remember that too many photons in the readout cavity excites higher order nonlinearities or will dephase your qubit or other qubits. And so really, this parametric amplifier boxed in yellow has hundreds of photons in it, and you want to prevent those photons from flowing back into your quantum computer. And this is what these circulators do. Now, one reason why superconducting qubits are a promising platform for quantum computation is that this setup, including the circulators and isolators, works relatively well. Well, at least with respect to what's needed for today's devices. So this dispersive readout, as you call it, has achieved a sort of 99% fidelity in less than 100 nanoseconds, and even higher fidelities in longer measurements. And of course, it's these are on single qubits. It's harder to get this good performance on many qubits, but steady progress is being made on that. But we also have to ask ourselves what will limit measurement performance in the future. And it's becoming increasingly important to think about the scalability and the quality of any measurement scheme. And so ferrite devices like these circulators and isolators, like the one pictured here, are really a roadblock, I think, when trying to envision systems with order 1,000 or more qubits. These circulators are problematic because they have limited performance, reflections, finite isolation, and unavoidable loss. They're also just bulky. So to put that in context, here's a photo of me pre-COVID times working on one of our dilution refrigerators. And companies like Google and IBM have larger dilution refrigerators, but maybe it's hard to imagine more than a cubic meter of space at base temperature. And if you're starting to promise a system with 1 million qubits a decade from now, I think it's really hard to imagine that if each qubit or every set of 10 qubits needs a device kind of like the one pictured here. You want some chip scale solution. And so in recognition of this problem, starting a little bit before my PhD, there's been a lot of work on how to replace these ferrite circulators with some sort of chip scale device, which is more scalable and higher performance. And it turns out there are many ways to create a non-magnetic circulator. Often these strategies involve parametrically coupling different resonant modes while specifying the relative phase difference between multiple pumps in such a way to break reciprocity. In 2017, we demonstrated our own superconducting chip scale circulator, also based on this some flavor of this parametric modulation concept. So that's the chip in this photo. It's really a 4-port circulator whose scattering parameters are shown here on the bottom right. So the blue and the orange lines are transmission versus frequency through the circulator as a function of whether its circulation has been tuned to sort of clockwise or counterclockwise. And as we can see, it works relatively well. We can see better than 20 dB of isolation over some tens of megahertz of bandwidth. And this device or other related approaches can certainly in principle be combined with a parametric amplifier to create a chip scale directional amplifier for qubit readout. But despite progress, it's fair to say that to date, nobody is close to throwing out their ferrite circulators and replacing them with any of these approaches, including ours. A common drawback is difficult calibration due to narrowband performance and multiple high frequency control tones. In our case, it was difficult to get the good circulator performance shown here while simultaneously getting high gain from a parametric amplifier, and not to mention doing this all at the narrow frequency of a readout cavity. So we took a step back and changed our philosophy. Specifically, we removed ourselves from the constraint of trying to build or even emulate a circulator or isolator. Freeing ourselves from this burden, we realized we could achieve a fast, scalable measurement using the coordinated operation of superconducting switches. To do so, we construct the device shown here, which we call a SIMBA, or superconducting isolating modular bifurcation amplifier. The SIMBA consists of a two-port cavity whose resonance frequency can be parametrically modulated to provide amplification, and where superconducting switches are placed on each port of the cavity in order to realize a tunable coupling. These broadband DC actuated switches, which we call tunable inductor bridges or TIBs, allow us to realize a swap operation between the readout cavity and the parametric amplifier by turning on and off this coupling with the first TIB. And so when we do our qubit measurement, we send a pulse into our readout cavity, do this swap operation, amplify the state in our parametric cavity or our amplifier, and then use the second TIB to connect our amplifier to a measurement chain and learn the state of our qubit at room temperature. And so doing that, we can get histograms that look like this. So blue is what I measure at room temperature when I prepared the qubit in the ground state, pink when I prepared it in the excited state, and they're well separated. So we can make this projective single shot measurement now using this approach, which has removed the circulators before the first amplifier. So in the rest of this talk, I'll tell you how we design our SIMBA, how we use it to measure a qubit, and how we characterize its performance. But first, let me stop and take questions for a few minutes, and also remind you to just don't be shy about asking questions as you have them. If there are no questions, then I can proceed.
I could ask a question if you want.
Sure.
Hi, nice talk, enjoying it. So I'm curious, how do you envision scaling these up? Because don't you need like multiple circulators and a HEMT after the SIMBAs? So will you perhaps time or frequency multiplex these?
Yeah, so I certainly think you could do that. I think in the sort of shorter term, the HEMT and the circulators are very broadband devices. I can probably multiplex like 10 or 100 qubits per HEMT. So I can still remove most of my circulators because I'm removing the ones before my first amplifier. I think in the longer term, you could sort of put switches before your HEMT instead of circulators, and time domain multiplex things. Yeah.
Thanks.
Yeah. So our SIMBA is a combination of a parametric amplifier and superconducting switches. Let me start by telling you about the parametric amplifier, which is simply an inductor capacitor circuit like the one shown here. And so this has a resonance frequency of 1 over the square root of inductance times capacitance. In our parametric amplifier, we realize much of this inductance with an array of squids. So this is two Josephson junctions in parallel forming a loop. And for the purpose of this talk, we can simply think of the squid as an inductor whose inductance is tunable with an external magnetic field through the loop. So we're going to tune this inductance. And so in this color plot here on the y-axis, I'm applying some DC bias control and bias signal into the cryostat and changing this resonance frequency in this arc-shaped pattern as a function of frequency. And so we can change our amplifier frequency between about 4 and 7 gigahertz. To operate the amplifier, we tune it to a specific place, say about 6 gigahertz, which is the frequency of our readout cavity. And then we turn on a rapid modulation at twice the natural resonance frequency, so about 12 gigahertz. And this will create a three-wave mixing process to realize phase-sensitive parametric gain. Now, this type of amplifier is common in our field, but is usually a one-port device with a circulator placed at its output. What's novel about the Simba is now this amplifier is a two-port device whose the external coupling rates of those ports are tunable. And now let me show you how we engineer this coupling using our tunable inductor bridges or our switches. And so you can understand these switches as conceptually similar to a mixer where the diodes have been replaced by arrays of squids, or again, tunable inductances. To create one of these switches or TIBs, these inductors are arranged in a bridge geometry called a Wheatstone bridge. The advantage of this bridge circuit is that it will allow transmission through the switch to be tuned by a far greater ratio than the constituent inductors can be tuned. This bridge has 4 nodes, sort of east, west, north, south, but the TIB has 2 ports. One port couples differentially to the bridge, to the north and south node. The other is connected to the east node of the bridge. And finally, the west node is grounded. And now to see why this is a switch, consider this differential voltage applied to the north and south nodes when the bridge is balanced as drawn, meaning that all 4 inductors have equal value. From symmetry of the circuit, there's a virtual ground at the right port, enforcing voltage to be 0 here so that a signal incident on either port will reflect. So maybe to say that again, when the bridge is balanced, there's an equal impedance across each arm of the bridge. And so if I couple differentially to the north and south nodes, there's an equal impedance across this inductor and this inductor. And so I have to have 0 here and enforcing this virtual ground. To put the TIB into transmit mode, we can imbalance the bridge so that the thick and thin inductors have different values. This breaks the symmetry of the circuit and eliminates our virtual ground, and therefore transmission will be non-zero. In fact, we can then engineer transmission to be close to unity by adding some capacitors to the network like shown. And finally, we will physically lay out the circuit by twisting the bridge into a figure-8 geometry. And this allows us to control whether the bridge is balanced or imbalanced by sending a signal into a single on-chip bias line. We could talk a lot more about how to engineer that, but let me jump straight to the performance. So in addition to integrating these TIBs into a Simba, we tested some just by themselves. So the measurement is very simple. We just cooled one down and measured in transmission. And so in this line plot here, the left y-axis shows transmission as a function of when the bridge is tuned to either a transmit mode or a reflect mode. And at the best reflect mode, we can see sort of less than minus 30 dB of transmission over several gigahertz of bandwidth. But when operating this TIB in conjunction with a narrowband cavity, we really just care about what is the on-off ratio just at that specific cavity frequency. At any given frequency, we can tweak the reflect mode bias just a little bit to improve performance. And that's the red right y-axis is the on-off ratio, the best on-off ratio we can get at a given frequency. And that's about sort of better than 50 dB between 4 and 7 gigahertz. By design, the same range over which the parametric amplifier can be tuned. So in addition to this sort of high on-off ratio as a function of sort of bandwidth, the switch has high enough power handling to process the signal in our parametric amplifier, and it can switch relatively fast. This along, with maybe a few other approaches, represents the state of the art for superconducting switches. And all of it is necessary for the experiment I'll tell you about next. But maybe to summarize the engineering behind this, we placed one of these TIBs on each port of our parametric amplifier to create a Simba. In this false color image of the chip, the parametric amplifier is at the center and the TIBs are on either side. And a lot of the complexity of this work is the sort of like layout and design challenges that go into making this chip, which is fabricated by our collaborators at NIST Boulder. And I'd be very glad to talk more about that, but for now we'll skip straight to the qubit readout performance. Unless there are further questions.
Sorry, I missed if you said what the speed was of the switching.
Yes, sort of nanosecond timescales. Yeah, I can show you some sort of data which sort of shows that in a little bit. But I think there's sort of a hard upper limit by the plasma frequency of the junctions, which is sort of about 15 gigahertz. That's sort of the where the junction is sort of no longer looks inductive. But below that, you're sort of limited by any filtering you might put in your BIOS line.
Thanks.
Yeah. So now let me show you how we use this device for readout. Because the parametric amplifier is a narrowband cavity, we must first tune it to the frequency of the qubit readout cavity. And so to do that experiment, this is sort of like step 0 when I cool one of these down. We have our qubit readout cavity with 2 ports, and I'm going to measure in transmission through it when both switches in the SIMBA are set to transmit mode. And then I'm going to apply an external magnetic field to tune the frequency of this readout, of the parametric cavity. And so that is the y-axis of this plot. I'm tuning the parametric cavity frequency, and I can see an avoided crossing where that parametric cavity tunes through the readout cavity frequency. And I want to operate generally where they're sort of maximally coupled, or at least in this demonstration, we operate where they're maximally coupled. And so, that's step 0. Now we're ready to measure the qubit. And so to do so, we first send a pulse into the readout cavity through this weakly coupled port. And remember, in the dispersive architecture, the readout cavity resonance frequency shifts by plus or minus chi, depending on if the qubit is in the ground or the excited state. And so we generally, as in conventional dispersive readout, we want to probe sort of in the middle of these 2 frequencies. A sort of nice feature of this is you can have a relatively large chi without being per cell limited, because when you're doing this, the TIB here is typically set to reflect mode. So you're actually in principle not introducing loss by having your cavity strongly coupled to the environment. So next, let's see. We switch the left switch into we put the left switch into transmit mode to turn on a coupling or turn on a swap interaction between the readout cavity and parametric cavity, swapping their states. So ideally vacuum in the parametric cavity and then some coherent state in the readout cavity. And importantly, the 12.5 megahertz coupling rate of this swap interaction is significantly larger than the loss rate of either cavity. And so we expect to lose little of the readout signal in this swap process. Next, we set the left switch to reflect mode and amplify the qubit state dependent signal in the parametric cavity. So this amplifier is a classical, we can think of it as a classical nonlinear oscillator, and we're actually going to operate it in the bifurcation regime. So when strongly pumped at twice its natural resonance frequency, the cavity field will amplify, but then due to some nonlinearity will latch into one of 2 bistable states. And these states have large amplitude but opposite phase. And so for the correct phase difference between the readout pulse and pump, which state the parametric cavity latches into will be highly correlated with the state of the qubit. Once we've completed this amplification step, we can connect the right switch to our measurement chain to determine which bistable state the parametric cavity is in, and hence complete our measurement of the qubit, at least at room temperature. And so these histograms, which we saw before, are really just examples of doing this procedure, many times and making some histogram. And a fun feature of this bifurcation amplifier is really that whether or not we measure, the state of the pumped parametric cavity will contain the classical information that's the result of our measurement for as long as we're willing to continue pumping it. This procedure is summarized by the timing diagram here on the bottom left. So there's sort of 4 things we do. Well, 5. We prepare the qubit in some state. Then we send in our readout pulse, turn on the swap interaction, turn on our amplification, and then connect our amplifier to our measurement chain. And as in any qubit measurement procedure, we generally need to calibrate the different steps, typically in order to maximize readout fidelity. So readout fidelity shown here is really just 1 minus the error probability of measuring the qubit in the excited state when you prepared it in the ground state, minus the probability of measuring it in the ground state when you prepared it in the excited state. Anyways, one important parameter to choose when calibrating this readout is the duration for which TIB1 is set to transmit mode. So in this plot on the right, we measure readout fidelity on the y-axis while sweeping the duration on the x-axis. So sweeping this swap step here. And so these oscillations show the readout signal swapping back and forth between the readout cavity and parametric amplifier. And for the fastest possible high fidelity readout, we generally want to operate at the first peak. And doing so in this demonstration, the entire measurement took 265 nanoseconds. And back to the sort of switching speed question, I think you can, the fact you can see these sharp features as a function of the duration for which TIB1 is set to transmit mode is sort of reflective of the fact that the TIB is switching on sort of a nanosecond time scale. I think each pixel in this plot is every nanosecond or 2 nanoseconds. And then, of course, eventually any signal you see sort of brings down because of loss in both the parametric and the readout cavities. So, looking back, we can see this sort of goes to about 90% here, sort of depending on exactly, there's some like drift in how I calibrate my pi pulse. And then, there's some residual excited state population and the qubit has a finite T1 time, and these all degrade fidelity. But I've thus far shown you a relatively fast and high fidelity projective measurement. But in the title of this talk, I also claimed high efficiency and low back action. And in this final section, let me explain these metrics and show you how we quantify them by using the qubit as a resource for metrology. So to describe this characterization, I want to digress for a minute into the concept of weak measurement in quantum mechanics. So here again, we have the block sphere on which I've drawn a qubit prepared in a superposition state, or equivalently this density matrix rho. We can measure that the qubit's in a superposition by doing a Ramsey experiment. So pi over 2 pulsing the qubit, waiting for a variable amount of time, then pi over 2 pulsing it again and making a projective measurement. If the pi over 2 pulse is a little bit detuned from the qubit frequency, we see oscillations as a function of this Ramsey delay. The amplitude of these oscillations measures the length of this arrow, or the amplitude of the off-diagonal element of the qubit's density matrix element, if you like. What we are really doing when we measure the qubit at the end of the sequence is we are first entangling the qubit with a readout pulse to create the joint state shown here, where in dispersive readout alpha 0 and alpha 1 are coherent states with the same amplitude alpha, but different phases. And in this experiment, they're close to 180 degrees apart in phase space because chi, we're in this limit where 2 times chi is greater than is quite a bit greater than the readout cavity line width when the TIB is in reflect mode. Anyways, so using our amplifier, we then projectively measure the coherent state part of this joint state, which necessarily dephases the qubit. So the qubit density matrix after our measurement rho prime is written here, where the off-diagonal elements are now alpha, the inner product of alpha 1 and alpha 0. And so if alpha 1 and alpha 0 are actually equal, say the vacuum state, so no readout pulse, then the qubit isn't dephased or even measured at all. That inner product is 1. If they overlap a little bit, then the qubit is partially dephased. And if alpha 0 and alpha 1 are nearly orthogonal, high amplitude coherent states at separate phases, then the qubit is entirely dephased and we've performed a projective measurement. And so after this measurement, we find that the qubit is simply dephased exponentially with the photon number of the readout pulses or the square of their amplitudes. And the takeaway here is that in quantum mechanics, we have this deep connection between measurement and dephasing, which we've now quantified for this specific case of dispersive readout. And so how does this relate to our calibration? Well, we control the amplitude of the readout pulse that we send into our cryostat, but we don't a priori know its photon number at the readout cavity. The first step is to learn this. So to express the strength of our readout pulse in terms of photons in the readout cavity, we're now going to do exactly the same Ramsey experiment we just saw, but with a separate weak measurement inserted into the delay. Now I use the word measurement here because inserting this step will dephase the qubit, but we're not actually recording any information about the qubit state yet, only causing some backaction or dephasing. Weak is also a misnomer because we're really going to vary the strength of this measurement between 0, so no dephasing, and a projective measurement, so full dephasing. And maybe this can make more sense by looking at the timing diagram of the different pulses we send into our system. So this first weak measurement has two differences from our projective measurement at the end of the sequence. First, we're going to sweep the amplitude of its readout pulse proportional to the square root of the number of photons in it, where we don't yet know this constant of proportionality. Second, for right now, we're going to turn off the amplifier pump in our first weak measurement to avoid exposing our qubit to any pump back action. And in fact, I'm going to start by turning off the first, any readout pulse in this first weak measurement too, so that we're only switching to TIBs. We then measure qubit coherence, so the which is again the amplitude of the cyan Ramsey fringes here, and those fringes are pretty similar to what we measure when we don't insert anything at all into the Ramsey delay purple. So purple is with nothing in this weak measurement step. Cyan is just with switching TIB1 and TIB2, and they're pretty similar. Now we begin to turn up the readout amplitude of the weak measurement. So in this slide, now the readout pulse is 1/3 the amplitude of our projected measurement, and the contrast in our cyan fringes goes down, meaning that the qubit has been dephased a little bit by the readout pulse. We then turn up the amplitude more, so here now 2/3, and the dephasing or the back action increases. And finally, our first weak measurement now has the same amplitude as our projected measurement at the end of this sequence. And as we expect, the qubit has been almost entirely dephased. We don't see fringes anymore. More quantitatively, we can express this dephasing as the amplitude of the qubit's off-diagonal density matrix elements after the weak measurement. And so the y-axis of this plot is the post-measurement coherence, rho 0, 1 prime, so that off-diagonal density matrix element amplitude, which is really a factor of 1/2 times the ratio of the amplitude of the cyan fringes divided by the amplitude of the purple fringes. So here, purple being the no weak measurement case, cyan being the with weak measurement case. And so now I am plotting, these data points are sort of what we measure as a function of this weak measurement amplitude on the x-axis. So the point I'm showing you here is this rightmost data point where the number of readout photons in the weak measurement equals that in the projected measurement. Here is the 2/3 case, the 1/3 case, and then finally the case where there's no readout photons. And from theory a few slides ago, we expect this y-axis rho 0, 1 prime to decay as a Gaussian with respect to the amplitude of this weak measurement. And indeed, it mostly does. There's actually some dephasing just from switching the switches, which I think is due to the parametric cavity not quite being in vacuum. But aside from that effect at sort of low low amplitudes, our data follows our model closely. And in quantum optics units, so here now we're working in sort of experimental units where NP is really like 2 volts on a mixer, and NR is some thing we're sweeping in volts. We can put that in quantum optics units by fitting a Gaussian to this data. So in these quantum optics units, this Gaussian should have a standard deviation of 1/2. And by doing that fit, we find that we calibrate this x-axis in terms of photon number, and we find that in our projective measurement, we're using about 2.5 readout photons. So that's great, but how does it relate to calibrating our isolation? Well, we can also do a very similar experiment here with no readout photons in this weak measurement, but with the parametric amplifier pump turned on. And that results in these dark blue cyan fringes, which are diminished in amplitude, and that's this point along the y-axis here. And so because we measure some dephasing by turning on the pump, and we've done this calibration now, expressed as a photon number, this corresponds to about 0.6 photons of back action every time we turn on the pump in our weak measurement, which is exactly the same as how we're turning it on in the projective measurement. And so this 0.6 photons characterizes our isolation. If you like to think of isolation in dB instead of in photons, from a different measurement, we find about 150 photons in the pumped parametric amplifier. And so our 0.6 photons of back action corresponds to about 25 dB of isolation. And that's a little bit better than one commercial ferrite. Usually use maybe 3 ferrite circulators, but so this 0.6 photons, we're maybe sad that it's not like a little bit closer to 0, but it's still only about 1/4 of the photons that we're using in our projective measurement. So when we make this projective measurement, most of the back action of our measurement is caused by this readout pulse we specify, not by some back action from the detector. So in fact, we can also use the experiment I just showed you to characterize the loss introduced by our Simba. And to do that, we have one final step. Let's now make a model for readout fidelity as a function of the readout pulse amplitude. So in our readout cavity, we have these 2 coherent states, alpha 0 and alpha 1, which are separated in phase space by twice their amplitude, square root of NR. And then we will swap these states into our parametric amplifier. But what if that swap step has some loss? Then these coherent states are diminished in amplitude by this factor square root of eta, where here eta is the measurement efficiency or quantum efficiency. It's really the fraction of energy in our readout signal lost before it is amplified. And so, for example, say our 2 coherent states are initially well separated in the readout cavity, but with enough loss, maybe they overlap by the time we measured. Our model for what our amplifier is doing is that it thresholds these coherent states using the y-axis here. And so this overlap leads to measurement error. Our model for readout fidelity is therefore an error function, this ERF function, which is the integral of a Gaussian from 0 to infinity as a function of the displacement of that Gaussian from the origin. So the displacement of that Gaussian from the origin, the argument of this error function, if you like, will depend on both the amplitude of our readout pulse and also this efficiency eta. And now we compare that model to our data by measuring readout fidelity while sweeping the amplitude of a readout pulse. And that's the right y-axis here. So fidelity, the data points does indeed increase as an error function. This line I'm fitting to it, relatively closely to our model. And it plateaus to about 95% because of our state preparation and fidelity. normally you would hope it plateaus to 100%, but our model includes that finite fidelity with this extra term out in front. And maybe the way to understand this is for say I have a really low efficiency, I need a couple of photons to do my projective measurement if my efficiency is perfect. But if I lose 99% of those photons, then I need like 100 photons to make a projective measurement. And so then I would expect this red line to increase very, very slowly. And of course, there's a limit to how quickly it can increase, because of course, if I make a projective measurement, I have to dephase my qubit. So if I measure a high readout fidelity at the same point that I have sort of post-measurement coherence, then I know I'm doing something wrong in my experiment. And so by fitting our model to data, we can extract the efficiency, and we find it to be about 70%. And to put this in context, the 70% is relatively high. For comparison, the highest efficiency I've seen in our field is from the Siddiqui group, where they measure an 80% efficiency in a system without any isolation between the qubit and amplifier. And for conventional dispersive readout using ferrite circulators, there are many examples of people getting about 10 to 60% efficiency. So now that we've seen the performance of our measurement, let me tell you about its limitations. So most of the readout infidelity seems to be a combination of a few percent thermal excited state population in the qubit, limiting our preparation, combined with a relatively short sort of 9 microsecond T1 time. So the qubit decays from its excited state to the ground state during our measurement or before our measurement. The fact we see some back action is telling us that our TIB isolation isn't perfect, at least in this combined device. One hypothesis for that is that the power handling of the TIBs is still a little bit close to the pump state in our parametric amplifier, and we can certainly design our TIBs to be a little bit more linear, a little bit more weakly coupled. Another hypothesis, one which is sort of easy to solve in principle, is that there's some, and we know this is there, is that there are cable modes between the readout cavity and the SIMBA. So, here's a photograph of our experiment, and the qubit is really just sitting in this metal box, this 3D cavity, which is connected via these microwave connectors to our SIMBA sample box, and that adds a few centimeters of waveguide between these two, which has standing wave modes with a free spectral range of a few gigahertz. And any signal we couple into those standing wave modes looks like effectively lost because it's not amplified. So anyways, we've been certainly working on our packaging to try to integrate this closer together to eliminate that source of loss and back action. Relatedly, the measurement efficiency of 70% is dominated by the 4 megahertz line width in the parametric amplifier. I think about 1 megahertz of this is just internal dissipation in the amplifier. We're using rather lossy squids, but the rest of that I think could be improved a lot by improving the TIBs and shortening this electrical length. And then finally, we can also measure a lot faster simply by pumping the parametric cavity a little bit harder. About 2/3 of our measurement time right now is dominated by the sort of amplification and digitization steps. That could potentially cause some more excess back action. So in general, there are sort of, in this demonstration, I picked one operating point where all 4 of these metrics seem to be sort of relatively good, but there are certainly trade-offs that can arise where you can get higher, better performance at something and less performance at something else. Anyways, in conclusion, we've engineered a chip scale pulse directional amplifier. We call it the SIMBA. And using this device, we demonstrate a relatively fast and high fidelity projective measurement of the superconducting qubit. So using a calibration based on weak measurement, we find that the SIMBA provides a little bit more isolation from amplifier back action than one ferrite circulator, and that it introduces relatively little loss before the first amplifier, with a clear path towards eliminating much of the remaining loss. From the scalability perspective, I also argue that the SIMBA is a favorable choice because it only requires 1 microwave bias line to operate just the amplifier pump. The TIBs can be controlled with low bandwidth signals. But here at the end of the talk, I want to de-emphasize the particular performance in this demonstration and instead promote the general concept. So as you well know, quantum science has this trade-off between isolating a qubit from its environment and coupling it strongly, sometimes to other qubits or a measurement apparatus. There's no fundamental reason that I know of why these couplings can't be tunable and something you can easily control. And so here we've shown that by engineering high enough quality superconducting switches, we can make some progress on some of the problems that plague conventional dispersive readout. But our approach is a little bit agnostic to the specifics of these switches. And also these switches, I think, have much more versatility than just this particular problem. So I look forward to seeing where these ideas evolve. And thank you very much for your attention. And I look forward to taking questions too.
Thank you. Let's open to questions. People can just go ahead and use the chat, or everyone should also have the security rights to unmute themselves directly.
It's good. Stefan, I'm not seeing the chat right now.
I can take care of it. So don't worry about,
Thanks.
about it.
I'm sure it's here somewhere. I think too many tabs open. Oh, here it is.
I had one quick question, which is I noticed in your weak measurement data, there was not only a dephasing, but also a phase shift. Could you comment on where that's coming from and whether it agrees with predictions and so forth?
Yeah, that's right. So essentially what that is doing is so the way I introduced this dispersive readout, it's like the readout cavity frequency changes depending on the qubit state. But sort of equivalently, the qubit frequency changes depending on the number of photons in the readout cavity. And so what we're seeing in this, let me just go back. What we're seeing with this phase shift here is that the, you'll notice this x-axis starts at 600 nanoseconds, just to give me time to put this weak measurement in here. In that time, there's this phase shift because the qubit frequency or essentially the detuning of my qubit pi over 2 pulse from the qubit frequency has changed a little bit because of this back action. And so I believe this phase shift we see does indeed correspond to the dephasing we measure here. So, maybe another way to see that is, the phase shift is changing as I'm changing this readout amplitude.
Yeah. Which is a more accurate way to estimate photon number, looking at the dephasing or the phase shift?
That's a good question. I believe them to be, like, in principle, they should be equivalent. And off the top of my head, I actually don't think I ever sat down and quite did what you're suggesting, but I believe that they're equivalent. That's a good thought.
Cool, thanks.
Yeah.
Hi, I have a quick question. This is Kevin O'Brien again.
Yeah.
So I'm curious, why did you guys use a 3D transmon for the qubit rather than something integrated on chip?
Yeah, that's a good question. I think there's two answers. The sort of, it is expedient to use a 3D transmon in that I can change the coupling rate between the readout cavity and the Simba by just I have some little antenna sticking into the cavity, and then I can take it out and change the length of that antenna very easily without fabbing a new chip. That's the sort of expedient answer. The sort of other general answer is that Conrad's prejudice, which is also mine, is that you really want to keep your amplifier module separate from your qubit module as much as possible, and so having we've sort of tried to marry ourselves a little bit to this modular architecture where the qubit is spatially distinct from the amplifier. And I think in the long term, you could debate whether or not that's a good idea. In the short term, I do think this experiment would have worked a little bit better if we just had a 2D transmon wire bonded to our SIMBA chip. It's maybe worth saying so this SIMBA is sort of made with this optical lithography process at NIST, and the junctions are several micron wide junctions with silicon dioxide between them. These are very lossy junctions, so you can't make a good qubit on the same chip as our SIMBA in our fab process. But I do think wire bonding two chips together would have worked pretty well.
Yeah, that makes sense. I share your opinion about keeping things modular and separate. I think it leads to fewer fab iterations.
Yeah.
Thanks for the talk.
Yeah.
Eric, great talk. So there's a similar concept used at optical frequencies in isolators. It's coordinated switches. I think of it as barn doors, sort of like opening in sync for signal to pass through.
Yeah.
But that approach has generally, so the drawback tends to be that the duty cycle during which it actually operates is limited to maybe 50% or something like this. What is that duty cycle in this superconducting device?
Yeah, so I think your duty cycle is basically limited by wanting your parametric amplifier to decay to vacuum by the time your sequence is done. You know, if I do a swap step where my parametric cavity is in some like thermal or like thermal coherent state, then I'll dephase my qubit and maybe reduce this. And that time is relatively quick because the coupling rate between the cavity and our measurement chain is very strong when TIB2 is connected. So there's sort of a 40 nanosecond ring down time of signal in the parametric amplifier I'm showing you the wrong data actually. Sorry, this is the 40 nanosecond ring down time is when we're not connected to the measurement chain, and that's like a 4 megahertz coupling rate. The coupling rate when we are connected to the measurement chain is 50 megahertz. So that's sort of more like a 10 nanosecond ring down time. So that sets the duty cycle. One of our sort of earlier ideas was actually we even have a theory proposal for this, which is a circular based on sort of these like barn doors, just as you said, of switching, but with sort of two arms. And so you keep one arm closed and the other arm connected, and then you switch them and there's some delay line in between. And that actually makes a very good circulator. It's just a little bit hard to engineer.
Gotcha. Yeah.
So.
And is the standard these days to use these magnetic materials instead, or?
Sorry, what do you mean by magnetic materials?
I mean if I understood correctly from the beginning of your talk, that these circulators presently, if you don't use the switches, they're based on.
Oh yeah. Sorry, these magnetic circulators.
Material of some kind.
Yeah. That is incredibly standard. So to my knowledge, like basically every experiment in our field, aside from the like sort of niche experiments like ours that are trying to replace these circulators, has 2 or 3 of these magnetic devices before their hemp amplifier, which is the amplifier at 4 Kelvin, which is sort of rather noisy. It's also, to my knowledge, every experiment that is trying to sort of scale up and has more than 1 qubit in their fridge only uses these ferrite circulators to date.
Yeah. Okay, but they're not so efficient. Is it the downside of it?
Yeah, so I think it is a very interesting question as to like how well you can engineer your circulators to be more efficient. So, in principle, there's some limit because these magnetic devices are not superconducting. And, so there's some like absorptive loss as you're passing through. I think that loss is sort of really only on the like 1% level. And I think most of the loss in people's measurement change comes from packaging losses. So if I have any reflection at the input of my circulator, that the circulator sort of routes it to some dissipative load, it doesn't just mean my coupling rate is a little bit smaller than. And so I really think that our efficiency in our field right now is limited by the sort of packaging, not by the actual circulators. That said, you know, they're also, I think it is very challenging to integrate them on chip with superconducting electronics because they have these permanent magnetic fields, and your superconducting electronics almost always has some loops that you want to be very careful about the magnetic fields you put in.
Gotcha. Yeah.
So, yeah.
Okay, thanks. That's very cool. If there are no other, how about other people? Otherwise, I'm going to ask another question.
Yeah.
Because okay, then I'll ask another question. So one other thing I was wondering about, just generally for qubit readout in superconducting systems, is that while you have very high fidelity 2-qubit gates, like the Google experiment, the Sycamore device is like, I don't know, 99.7 or 5 or something like this 2-qubit gate fidelity, but then the readout fidelity is not good.
Yeah.
Why is it not? Why could you not, for example, take a qubit and use some sort of a repetition code where you use a C0 on a couple of qubits to create, superposition of the state, and then you have multiple single microwave photons that you have to read out for state 1 or 0. If the gate fidelity is so high, why can't you sort of amplify the state that way?
Yeah.
I'm talking about like making a GHZ state or something.
Right. Like if I understand what you're saying, it's like, say, my gate, if my 2-qubit gate fidelity is a lot higher than my measurement fidelity, why not prepare sort of 111 plus 000 and then measure all three at once, and I know that lets me sort of like check my measurement.
And then you have some Bayesian model or something to exactly. The majority voting or something. Yeah.
I certainly think you could do that. I think, then fitting sort of more than like 100 qubits in the cryostat is the state of the art right now. So I think you're probably, at least in the short term, better off like trying to like improve your readout fidelity, which I think in the state of the art experiments is maybe limited by the transmon T1 relaxation time.
Gotcha.
Yeah.
Cool. Yeah. Stefan, what's our schedule?
If there are no other questions, maybe we can continue to the various breakout meetings that Eric graciously agreed to. I see that Kevin just unmuted though.
Yeah, just a quick comment. Like, this conclusion about T1 limiting the readout fidelity, this applies to this work as well. Like, your scheme could have achieved 99.9 if you had a longer lived qubit. So
I think that's right, with the exception that I have a couple % thermal excited state population. And this is sort of a detail you might appreciate. My Q and D fidelity is a little bit lower than my readout fidelity, and I don't know why, but that lets me not do state preparation by measurement. But those two things, like in principle, shouldn't be true, and other people have shown they're not true. And then you're exactly right. Yeah.
Gotcha. Awesome. Thanks a lot. Really great talk.
And thanks everyone for joining us today. And that's all that we have on the public schedule. See you next week.
All right.
And let's wait a minute or two and start the breakout rooms.
Great.